Hello, welcome back. Today I want to talk about the common mousetrap. I want to film it in slow motion and watch it destroy various things, for lack of a better word, but then talk a little bit about the physics behind what's going on. So after we show it in slow motion, we'll talk about kinetic energy, we'll talk about potential energy, and how this very common contraption actually works. Now, the first thing I'm going to say is do not do this at home because you can hurt your finger. So here is the common mousetrap. Rule number one, you only want to handle one side of the mousetrap. You see this side, that's the side that hurts. And so you want to get your fingers, keep your fingers away from that. So you only handle from this end. Of course, I don't want you to do this. I want you to watch me do it so you don't have to do it yourself. But when I'm handling it, I'm only handling it from the side. So if I accidentally let it go, then my fingers are not in the way. So that's your safety tip there. Now you have to hold it, and you do have to kind of like be a little bit in the way here as you trigger it. But again, my fingers are on this side, and I'm going to release it very slowly. Make sure it's got good tension. My fingers are out of the way. And then after it's set there, you never, ever, ever put your fingers on this side, ever. That is your rule of thumb. Don't ask me how I know. I didn't actually slam it at full force, but I got pretty close. So here's a mousetrap, and just to show something else on there, just have something to look at. We're going to trigger it by pushing down on this side right here. So it'll be like this. Or I guess I'll do it on this side. 1, 2, 3, and push down gently, and there it goes. You can see that this process, this slamming of a mousetrap, happens very, very, very fast. I actually can't even see it with my naked eye when it triggers like that. Now, it's a common household item, right? But how does it actually work? So first, let's go take a look at the slow motion clips. I wanted to show various situations and really see what's going on. Then we'll come back and talk about the science behind what's actually happening.
Now, the first thing I did was trigger the mousetrap with a pencil. This shows the incredible force involved. When we get right up on top of it, you can see the pencil lead snap. For the next attempt, I put a potato chip in place, which got launched and split in half in the air. A total accident, but a cool shot. For the next attempt, I put the chip back in place, but positioned it so that it did not get launched in the air. As the bar on the mousetrap slams down on the chip, in slow motion you can really see the release of potential energy coming from the spring as it slams down on the chip and shatters it into thousands of little pieces. And what's interesting is those pieces tumble and twirl as they go out from the point of impact. Ultimately, the potential energy in the spring is transferred directly into all the pieces of the chips flying around. I wanted to try something resembling human flesh, so I picked up this cherry tomato. Now, it didn't split the tomato in half, but you can see it made a pretty nice indentation. If you could imagine this being your finger or some other fleshy bit, it's really going to hurt. Now, I think the most impressive part is when I did it to a grape. It split the grape clean in two, splashing out grape juice from the inside. What's amazing about this is when you really zoom in on the grape and look at how it slices through, it looks a little bit like Fruit Ninja, where this blunt-looking bar makes a clean strike right through the flesh all the way through, spraying out the insides. I wanted to do something that just flew everywhere, so I picked up some glitter and sprinkled it on the end. And you can see as soon as the bar slams down on the glitter, the base actually lifts up and throws the glitter in the air and disperses it in thousands of little sparkly pieces. And here's the final shot where I put my zoom lens up, and you can really see microscopically the kinetic energy of this mousetrap going into the motion, but more importantly into the rotation of each of these individual flakes of glitter. And that's the whole point of this thing anyway, to visually get a feel for the transfer of energy from potential energy into kinetic energy.
Well, the big picture here is that this mousetrap consists of a bar connected to a spring. It's very tightly wound spring, but usually we think of springs that we expand and contract. This one isn't doing that. It's basically going into a more coiled up state. And then when it slams back, it's unwinding that potential energy and going into the open state like this. So it's not stretching and going back, it's winding the spring up and then releasing it. So it's kind of like a torsional tension there, to use a big fancy word. So how does it work, right? There's a lot that we can learn from this because it involves the concept of energy, right? Energy is this thing that most people think they know what it means, but in physics or in science, it has a very specific definition. There are two main kinds of energy. We have potential energy, which is the potential to do something, but nothing yet has happened. That would be what's going on whenever this thing is in the ready to slam state, right? Has the potential to do something, but nothing much is happening yet. And then we have what we call kinetic energy, which is the energy when something is actually moving. So whenever we have this thing ready to go, it has a very high potential energy. And then as we release it and it begins to move, the movement of this bar in the downward direction, while it's moving, we say it has kinetic energy. So the big picture that I really want you to get across from no math point of view, but just from a big picture standpoint, is these two kinds of energy can be converted from one form to another. When we pull this thing back, notice I'm only holding it at one end, it has a very high potential energy. When we release it, the potential energy that was stored as the spring was coiled up, it is released and converted into kinetic energy, the energy of motion. And then as it gets into to the final state there, all of the potential energy it had is now gone, and that was then converted to kinetic energy of the motion of this bar. Now you might say, well, once the bar hits the bottom point, what happens to all the kinetic energy that was there? You see, in the universe, energy is not created, nor is it destroyed. It is only changing forms. So again, initially it's potential, then it goes to kinetic energy, but once it stops, where does the energy go? Well, you can hear it, right? Listen to the sound, right? That sound, as the wood is impacted by the metal, is from sound waves because of the vibration of the wood as it slams down, vibrates the air, and the vibration of the air travels as a wave. And so the energy of the motion of that mousetrap bar gets ultimately converted into sound waves, which we hear. And also, it's vibrating the wood. And so if you had a microscopic, temperature gauge on this wood, at the point of impact, we would see the temperature of the wood go up a little bit. So the energy goes from potential energy into energy of motion of the mousetrap metal. And then when it hits the wood, it is converted to heat in the wood, in the mousetrap base, and into motion of the atoms, which we hear as sound. Now that energy is not destroyed either. It is just transmitted throughout the universe or throughout the Earth's atmosphere and eventually goes into the energy of the motion of all the atoms and molecules in the room and so on. So energy is not created or destroyed. We call that the law of conservation of energy. So that is the big picture, potential energy, kinetic energy, but of course I want to go a level deeper. It is not a complicated discussion, but it's a very important discussion because in physics and in science, and even in chemistry and even in biology, any branch of science that you study, you will constantly be dealing with energy. When you eat things, you have energy in the chemical bonds of the food converted into energy of motion of your body, right? When you burn things, you have, again, chemical bonds in the wood and the air, which are broken down, and that comes out as heat and light. That's a conversion of energy. You even have a conversion of energy in nuclear reactions and other things too. So conservation of energy, energy conversion, very, very important. So the easiest way, in my opinion, to really go a level deeper is to talk about something that we have some familiarity with. So we have a roller coaster here. It goes down, and then it goes up to some other height here, and then it goes down, and then to some lower value like this, right? So we can imagine some kind of car on top of this roller coaster, and it's traveling this way. It's going to go down, then it's going to go up, and then it's going to go down. Eventually, it'll come to rest when we hit the brakes or when the friction with the track basically slows it down. It stops it here. So at some point in the future, we're going to have the car here, right? As it goes up. At some point later in the future, we're going to have the car here, and then eventually the car was going to come here, and I'm going to say this is at rest. Now, in reality, there might be a very long track at the end where it slows down, but we're just going to say that it's at rest right here. So this concept of potential energy and kinetic energy. For the mousetrap, it was the coiling up of the spring, right? But in actuality, we have a situation where we have other kinds of potential energy. Other examples would be the distance above the Earth. That the higher we are above the Earth, the more potential energy we have. If you're standing on top of a house, then you have a certain amount of potential energy. If you jump off, then you're going to fall down, you're going to do some damage. But if you're standing on top of a skyscraper building or an airplane and you jump out, you're going to do a lot more damage. You have higher potential energy the higher we are above the ground. So in the case of a roller coaster like this, at this point, this maximum height here, we're going to be h meters above the ground. This thing is the ground level. Actually, the ground is a little bit lower. The ground is over here. Something like this. Sorry about this marker. Right? So that's the ground level. So here we're not quite at ground level. And what we say is that at the maximum height above the ground, we have a very low kinetic energy, that's Ke, but a very high potential energy, the highest, in fact, because it's directly related to how high you are above the ground. But now we've gone to a lower position above the ground. And at this snapshot in time, now at this height above the ground, we're going to have a higher kinetic energy, higher than it was right here, and we're going to have a lower potential energy, right? Because we're picking up speed. We're going faster, faster, faster. So kinetic energy is related to speed. And so we're going to have a higher kinetic energy, but we've traded. We've given up some of our potential energy and converted it into kinetic energy. Once we get up to the top here, then we're going to have some sort of medium. I'm going to call it medium kinetic energy. And we're going to have some kind of medium potential energy because we are going slower than we were, but we also are higher above the ground, so we've gained back some of our potential energy. Now, when we're over here at rest, we're going to have a very low, or a very, I should say, highest kinetic energy, right? And we're going to have a low potential energy. Actually, we're going to have zero potential energy because this actually is ground level. You can't fall any farther through the ground. So this kind of makes sense with what we already know. When you're at the top of the roller coaster, you're going the slowest speed, lowest kinetic energy, but very high potential above the ground because you're way high up. This is like coiling up a spring. As you go down, you pick up some speed and you go to a lower potential energy state. But as you go back to this higher place, you are a little bit higher in your, or lower in your kinetic energy, slower speed, but you've gained some of your potential energy back, so it's medium, medium. And then when you go to rest down here, your kinetic energy is the highest, you're going the fastest, but your potential energy is the lowest. Now, eventually the track will grab you. I'm talking about right when you get to the bottom of the hill, you're going the fastest. So this is a balance of kinetic energy and potential energy that we have very, very, very good experience with. Now, the important thing to note here, right, is that the total energy of the system, not kinetic or potential, but the whole entire thing, the total energy of the system is the kinetic energy plus the potential energy. We just add those two things together, and it is what we call a constant. You may have heard the constant, the law of conservation of energy. That means energy is not created or destroyed, only changed or transformed from one form to another. What I'm trying to say is at the very beginning, we have a total energy of the system. It's equal to whatever the kinetic energy is. And as this car goes in various points along the track, sometimes the potential energy is lower, but then the kinetic energy has to be higher. And sometimes the kinetic energy is higher, like at the end, but the potential energy is lower. But it will always be the case that if you add up the kinetic and the potential energy at any point in time on this whole track, it will be a constant number, whatever the total energy of the system is, given by that initial height above the ground. You're just trading forms, kinetic energy changing to potential and back and forth. And that's the same thing that was going on with the mousetrap. The total energy of the slam is related to how much potential we gave it in the beginning. And we can also see it in these other, this other little situation here with this paper clip here. So if you take a paper clip like this, it's just a regular paper clip. If you bend it out like this and bend it kind of in this little triangle like this and kind of bend it back like something like this, and it helps if you have one of these, one of these rubber coated or plastic coated ones. And if you pinch this guy together, and if you're very careful, you can get it to not fly apart. But then when you drop it, well, if you drop it properly, If you slam it, let's try to slam it. There we go. And see, it pops up like that. The potential energy was stored in the elasticity, or in the force here that you're feeling, the spring back force of this metal. And then when we triggered it to be released, that potential energy was converted to kinetic energy, and it propelled it up into the sky to some maximum height. What do you think the maximum height corresponds to? Some potential energy above the ground equal to the kinetic energy that it started with to begin with there. And so it's always an interplay, a transition between kinetic and potential, and kinetic and potential, whether it's a mousetrap, a roller coaster, or something else like this thing here. Now, in science, we like to talk about springs, and the spring is what we is in that mousetrap over there. So we'll and the springiness of the paperclip as well. So you can think of a spring. You can think of the natural coiled state of a spring, and this is what we would call low potential energy, because it's just kind of sitting there. It's not stretched or compressed, and so it's not going to do anything. So it has a low potential energy, maybe even zero potential energy. Now, if you take that same spring and coil it real tight, like this, so you squish it up like this, and you do that by applying some force in this direction, by pushing it up like this, then we say that it has a high potential energy. And it has a high potential energy. Why? Because it has the potential to do work, or to move something. If I let this thing go, it's going to go boing like that, right? Now, what if we go the other way? Instead of compressing the spring, what if we expand the spring? Like this. We stretch it out like this. Well, same thing. I do that, but the opposite direction. I pull it in the opposite direction. But when I let it go, it's going to bounce back. So it has the potential to do some kind of work. So we're going to call this, again, high potential energy. Wrote PE twice. High potential energy. Right? The point is that when you compress or expand the spring and then let it go, it's going to begin to move. It's going to convert that potential energy into motion, which is kinetic energy. Eventually, it'll boing back and forth, converting back and forth into potential and kinetic forms, and eventually it'll stop. And the only reason it'll stop moving is because there is friction internally between the atoms in the spring, and the rubbing will slow it down over time. But that energy goes into the thermal motion and agitation of the atom. So it's not like it disappears. It just goes into what we call the temperature of that spring. If you do that enough, even if you bend a metal back and forth over and over and over again, you'll see that it gets hotter like this. So we convert potential to kinetic energy in springs as well, and that is what is happening in this mousetrap right here, and that is also what is happening when we have one of these one of these paper clips that we bend out of shape and have it build up like that, or bounce up. So I think I want to talk lastly here about why do these metals have a spring back effect anyway? Like, why isn't it like water? If you try to stretch water, it just kind of falls apart, nothing happens. Right? Why is it that metals, when you compress them, tend to spring back, or if you stretch them, they tend to spring back the other way to some natural kind of like state? Why is that? Because that's the basis of a lot of machinery. Suspension in cars, springs, lots and lots of things. Anything that bends, it's only going to bend to a certain point. If you bend it with too much force, like for instance, this paperclip here, you know, I can bend it into this triangle shape. And if I bend it in this triangle shape, if I pull it apart and let it go like this, it's going to spring back to where it was, right? This mousetrap, if I pull it back, it's going to want to go back to where it was. But if I take this triangle here and I bend it too far like this, it doesn't want to go back. But up to a certain degree, it wants to spring back to where it was. But if I exceed whatever critical amount of force that is, then it doesn't want to spring back anymore. Why does that happen? So we're not going to do a whole material science lesson, but I'll just tell you that metals, most metals, in fact, almost all metals are actually what we call crystals, right? Crystals. Now, we normally think of crystals as like, you know, crystal chandelier or crystal salt. Salt is a crystal. Or, you know, anything shiny and sparkly, diamond, you know, we think of those things as crystals. But actually, metals are crystals too, with very few exceptions, right? A crystal just means that the atoms, or well, in the case of metal, it's atoms, but in general, it could be molecules. But for certain situations, alloys and things like that. But let's just talk about pure metals. The atoms there are arranged in a very regular arrangement of a lattice. They're bonded together in a lattice type of structure. So in other words, in aluminum or steel or whatever it is, they're not randomly bonded together. So if it's aluminum or something, you know, you may have an aluminum atom here. I'm just drawing it as a single circle, okay? We know it's more complicated than that. Another aluminum atom here, another one here, and they're going to be arranged in some sort of lattice, some sort of regular arrangement of atoms. Now, in reality, you know, lattices in crystals like diamond and also in metals, it's more complicated than I'm drawing it here. It's not necessarily a grid like this. But whatever it is, it's a three-dimensional thing. So it would be going into the board with these atoms and out of the board as well. But let's just visualize it like this. Now, keep in mind that this is a nucleus plus an electron cloud. A nucleus plus an electron cloud. And don't forget that the electrons repel each other, right? And so those are the edges of the clouds. And then the nuclei, which are buried way on the inside, like very, very tiny on the inside, if you get them close enough, they will repel each other, okay? So oversimplification here, because quantum mechanics really doesn't obey common sense, right? But you can get an idea here. What's going on is these are bonded together, right? And what's going on is if you try to if you literally push it, like if I'm going to take this metal and compress it, bend it toward each other like that, then these atoms are all going to be pushed closer together. Now, the electron clouds will overlap more and more if the nuclei get close enough together, or if the electron clouds get close enough together, then there's going to be a repulsion there, right? And so if you try to overlap them too much, they're going to try to spring back. That's the origin of the force there when you compress something, why it would like to spring back. Now, when you pull it the other way, if you try to pull this thing apart, it tends to spring back to its default state because these are bonded to each other in there. And the chemical bonding or molecular bonding is not something you can describe in a few minutes here. It really obeys the laws of quantum mechanics, but basically the electrons are either shared or transferred in a substance, right? And that is a quantum effect. And so when you pull them apart, they're trying to go back to their normal default distance of where they like to bond there. So if you push them too close together, the electron clouds are repelling, and if you pull them too far apart, the bonds are pulling them back. And so this metal is always wanting to be in that state. Now, if I pull it too far so that it basically is disrupted so much that the lattice gets broken or rearranged in some sort of other way at the point at which I'm bending it, right? Then the restorative force is not going to work anymore if you bend it so far that I'm literally ripping the thing apart. You disrupt the lattice at that microscopic crack there. And if you bend it back and forth over and over and over and over and over again, like I could do with this paper clip. See, this is a pretty thick paper clip, so I don't know. But if I bend it back and forth over and over and over and over and over again, then I broke it. Right? And it also it's kind of warm to the touch right here. And that's because I'm basically breaking the lattice and over and over and over again. Eventually I weaken it so much that I can pull it apart. All right, so that's an overview of kinetic energy, potential energy, and converting between them. Applies to mouse traps, applies to these neat little bouncy things that you can make with paper clips, applies to almost everything in the universe, actually. So I'd like you to please let me know what you think. Please drop me a line. Tell me, do you want more detail, less detail? Tell me what you want. I read every single comment, and I'll see you in the next one.
Learn anything at mathandscience.com.